Oh, uh, all right, guys. Welcome back to another week of interactive session of the course Viscous Fluid Flow, and we will begin from where we left it in the last week. So, if you remember, in the last week we solved a 2D problem involving solving two components of velocity field u r and u theta, if you remember, and the basic problem. I'll just recapitulate it once again. So hold on for a second. Yeah. So the basic problem was that we had a cylinder which was rotating in the counterclockwise sense with some angular velocity omega, and the complexity in the problem lies in the fact that now, in addition to the rotational motion imparted by the cylinder was also porous, and as a result, there was a radial suction which we call it as U, which was taking place at the surface of the cylinder because of the fact that the cylinder was porous. And that's the reason why we solve for the two components of velocity. If you remember, it was u theta and ur. We considered certain assumptions. For instance, we considered the fact that the cylinder is infinitely large in the z direction, meaning that the variables are independent of the the variable z. That's the z direction that we didn't consider in our analysis. And the problem was axisymmetric in nature, meaning that we did not that all the variables, if we move around the z-axis, all the variables is just the same. That is, they are invariant if we just move around. Basically, if we just move around this z-axis, that is, the flow field is identical if we and or in other words, the flow field is not a function of theta, and that's why all other variables, for instance, like the pressure and all other like pertinent variables were independent of theta. And that's the reason we considered that's the reason we considered the fact that my flow field is axisymmetric in nature. So if we consider these two assumptions, we saw that the velocity field which we are solving for, that is u theta and ur, those were just function of r, and that simplified our analysis to an extent. And then what we did is, our objective was to first use the and of course we are solving the problem non-dimensionally. Then the objective was to use the characteristic scales that were given in the problem, because of the fact that we have two independent mechanisms. One, the radial suction at taking place along the surface of the cylinder, and the other, the cylinder was itself rotating with an angular velocity of omega, because of which there were two mechanisms which were driving the flow. The question asked us to basically evaluate to basically use the two different scales of velocity corresponding to these two mechanisms, and then derive non-dimensional uh, variables, for instance the velocity field and all other variables, using the prescribed characteristic variables given to us. And using that, our objective was the further objective was to derive the non-dimensional governing equations. And that's what we did. We used the characteristic variables to basically write down the non-dimensional equations by first defining the non-dimensional uh, variables like ur bar, u theta bar, and p bar, and so on and so forth. And then what we did is we evaluated the simplified r momentum and the theta momentum equations. If you after successfully doing the math. Now, herein we saw a challenge. The challenge was that when we wrote the r and the theta momentum equation, we saw that these equations are indeed coupled, meaning that the unknown velocity u r bar and u theta bar along with pressure appeared simultaneously in the r momentum equation and as well as in the theta momentum equation, meaning that we also need one more set of equations to basically get the unknowns which were kind of coupled here. Okay, and for that what we did is we used the most convenient equation at our disposal, that's the continuity equation. And we use the continuity equation to basically calculate what would be my ur, and luckily we saw that using the boundary conditions that were given to us, ur came to be equal to minus of 1 by r bar, where all the bar quantities are non-dimensional, as you know we just saw in the analysis. Now, once ur bar is known, we use the theta momentum equation to basically calculate u theta bar, because of the fact that in the theta momentum equation, the only unknowns that we now need to solve for is u theta bar, because ur bar is already known, and this is which is equal to minus of 1 by r bar. So that's the only unknown. So this is the only unknown that was required to be solved, and we solved that. And what we saw is we inevitably ended up getting something which is known as an Euler-Cauchy equation, and we solved this Euler-Cauchy equation to basically calculate the form of u theta bar, and u theta bar came as something like this. And then what we did is, in order to evaluate the constants a1 and a2, we used the boundary conditions, and we had two boundary conditions. Remember, that is one, no slip on the particle surface. That is the u theta will have a velocity of omega times a, and non-dimensionally it will just have a velocity of 1, because my characteristic velocity was itself omega times a. So that means u theta bar at r bar equal to 1 was just 1. And at far field, we know that the velocity, all the velocities that basically are a result of the disturbance generated by the cylinder, which itself is rotating, and there is a suction, and all these disturbances go to oblivion as r tends to infinity. My u theta bar also goes to 0 as we move farther away from the cylinder. And from these two boundary conditions, we saw an important conclusion, which basically will form the basis of today's analysis, and then we will see the next agenda of today's discussion. Okay, so what we saw is that we saw that in the expression that is given by equation 5, we saw that for Reynolds number less than 1, given the boundary conditions we had, we could derive unique solutions based on the boundary conditions that were given to us. But for Reynolds number greater than 1, the said boundary conditions were not sufficient to give us unique closed form solutions, basically, at least by using the boundary conditions that we have at our disposal. Which means that for low Reynolds number flows, this analysis, that is for exactly for Reynolds number less than 1, the analytical methodology will give us unique solutions. But then for Reynolds number greater than 1, these form of solution for ur and u theta does not hold good. And then what we did is, okay, for Reynolds number less than 1, we also evaluated pressure. And the way how we did that is, like, we inserted the ur and u theta expressions of velocity field into the r momentum equations, because recollect that in the r momentum equation we have pressure, because pressure will also vary along the r direction, and that's the only direction variation of pressure is possible. So what we did is, we then evaluated pressure by just integrating the r momentum equation once with respect to r, and then using the fact that at far field pressure is just a constant value p naught, which gave us an equation, you know sorry, which gave us the solution for pressure of this form, to be precise. Now this is from where we will start, and we will end this discussion, and we will see what are the subsequent discussions that we will have. But for now, like, we will begin from the point where we left at last class. We evaluated the pressure field, but we are in the regime where Reynolds number is less than 1. And I gave a hint that a stronger criteria for exact solution is possible if we consider something which is known as the circulation to be finite at far field. Basically, what I mean to say is that, so before using this criteria, in order to find a more stronger solution, I say it's a more stronger solution, because still we will see that once this analysis is completed, we will see that it won't give us the exact solution for all the parametric spaces of the Reynolds number. No, that still won't be possible. But we will kind of move a step ahead, like in the parametric space of Reynolds number, and we will see that instead of now Reynolds number, you know less, less than 1, we will see that for Reynolds number less than 2, this analytical form, using the fact that circulation is finite at far field, is sufficient to give us closed form analytical solution. And this is something that we will see. But still, for Reynolds number greater than 2, the form of solution based on this boundary condition is still not sufficient for us to give unique solution, and that we will see subsequently. But before that, if you have any doubts uh, based on whatever we saw in the last week's interactions, or any doubts associated with the assignments, or the lecture series, please feel free to either ask here, or like post it in the discussion forum as and when you encounter that doubt. But still, I'll wait for a couple of minutes for you guys to set in, and then we will see the stronger criteria for finding exact solution of this analysis. All right. So what we will now do is I will first state what circulation actually means, and before using this circulation boundary condition as a before using this circulation as a boundary condition. So when I say circulation in fluid mechanics, or it basically means that if I have my velocity field and I integrate this velocity field along a closed curve, this is precisely what circulation basically means. Okay, and that's the definition of circulation in fluid mechanics, of course. Okay, and in other words, you can say in the let's say in terms of a more generic mathematical description, you can say that if you have a vector field, okay, and then if you have a closed curve, if we basically have a closed curved, okay, that's not a closed curve, sorry. So basically if we have a closed curve and then you have a vector field facing in any direction, and then you integrate this vector field. If you integrate this vector field along this closed curve, it basically gives you circulation. Okay, for instance, like the dl is basically going to be something like this. This is what dl bar will look like. Okay, now if you just integrate this integrate this particular vector field along this closed curve, this will basically give you circulation, and mathematically this is what it looks like. Okay, now in fluid dynamics, this vector field happens to be our velocity field, and we will mostly be dealing with velocity fields, and that's why I will call this vector field as velocity field only. So in fluid mechanics, if you integrate the velocity field along a closed curve, you will basically get the circulation. That's the idea. Now what what this says is that, so the boundary condition that we'll be using is that it says that circulation remains finite at far field. That is, if we move away from the cylinder, my circulation is finite. Now let's use this statement as a boundary condition. So what I will do is, first let's let's first draw our cylinder. Okay, so basically we have this cylinder. So we have this cylinder, let's say. Okay, and I'm drawing in the r theta plane, meaning that my z is perpendicular to the plane where I'm drawing the figure. uh, and now this, let's say, is my r, you know is my radial cylindrical, is my radial direction basically. Now what I'm saying is that if I consider a radius, which is, let's say, very far away from the cylinder. Let's say this is r greater than infinity. I define a closed curve along which I'm trying to basically evaluate my circulation. Okay. Now there are multiple ways by which I can define this closed curve. See, the idea is I'm just trying to use the boundary condition that my circulation is finite. Now, if I want to define circulation at a distance which is far away from the cylinder, I need to define a curve. Now there are multiple ways, in which I can define a closed curve. I can basically make any arbitrary closed curve something like this. This is also equally, this also equally holds good. Like I can make any random closed curve to basically evaluate the circulation. But I'll not just make life so difficult for us, because in order to just evaluate circulation, I can just make a closed curve which is kind of like a concentric circle. Or you can think of it like it's in 3D space, it's kind of a concentric cylinder, or in better, I would say that in the r theta plane, my closed curve is kind of a concentric circle, and this is along which, and it's along this concentric circle I will evaluate my circulation, because that's an easier thing that I can think of. Because in whichever way I define my curve, the ultimate objective is that I want to have my circulation to be basically to be a finite quantity. So what I will do is, and we will see the advantage of just using, and the advantage of just defining the closed curve to be a circle is obvious, and we will see that very shortly. So what I will do is I'll define a closed curve, you know maybe something like this. Okay, and this curve is basically rotated is located, let's say, at some radius rs, where rs is very much larger than the radius of the cylinder, which is a, meaning that we get rs when r basically tends to infinity. Or you can say that rs is just, so r when tends to infinity is just some rs. Okay, now along this closed curve I can have my velocity field. Okay, I can have my velocity field, let's say v bar. Okay, and then in order to define circulation, I must also define the dl bar, which is the vector which denotes the infinitesimally small length along this closed curve, and this is what dl bar will look like. Okay, but recall that since my closed curve, since this closed curve is a circle, okay, that means I can just say that dl bar is just dl e theta hat, where my theta is basically this is so how do I say, okay, so this is r, I will say like this this is any generic r, this vector, this black vector is er hat, that we all know, that's the that's the cylindrical radius that I'm saying, and this is and er hat basically denotes the unit vector in denoting its direction, and then I have this is what e theta will essentially look like. Okay, so the point is that I'm choosing a closed curve which is circular, meaning that dl bar is just going to be dl times e theta. Now, if I define circulation based on this, based on, so the idea is I will now define circulation along this chosen closed curve, which is nothing but a circle. Okay, so then I can say that gamma, which is my circulation, is essentially, you know, it's basically line integral of uh, v dot dl around this closed curve, but I know that my v is nothing but er hat, that's the velocity field, plus u theta e theta hat. Okay, and then I do this dot product, and this is also a vector, and this is done with dl e theta. Okay, that's because I have defined my closed curve, and here we will see the what I would say, the important, it's not important, but it's like the feasibility of defining my closed curve as a circle. This simplifies the definition of circulation that we are going to use. Basically, that's the idea. So the point is that I can now define my dl bar. I can now define my dl bar as just dl times e theta, because of the fact that the closed curve that I'm defining is just a circle. Okay, and then if I do this dot product, what I will get is I'll just get gamma, okay, as u theta dl. That's it, because the dot product with r, this will just vanish away. Okay, so and of course there is this integral. Okay, now let's see what this dl would look like. So dl would now be simple, because like I can always, so what is DL? Okay, let's do it here. I have already defined DL. So DL is basically this infinitesimally small length, and it's the magnitude of that, right? So what that would be? This would be like some R, okay? And then I know that this subtended angle is just going to be d theta. Okay? So my DL will then just turn, and this is close integral. Okay, so then I can just write it down as close integral of u theta times dl is just r d theta. Okay, and remember that my gamma, okay, which of course will be a function of r, this is just, so remember u theta is just a function of r, and then we have this r, and this is d theta. And now from where I'm integrating, so I need to integrate this d theta from 0 to 2 pi, because I want to integrate. So if I start from here, I must come back, I must move around this point, and I must just come back here, because I'm doing a close integration along this, along this curve basically. So I can, so this means I just need to integrate this now from, so gamma r is just going to be integration from 0 to 2 pi, okay, u theta, which is a function of r, and then d theta. But remember, this u theta times r, this is not a function of r. This means this will come outside the integral, and then this will become gamma, which is a function of r, and this will just going to be 2 pi 2 pi r u theta, which of course is a function of r. So this is how I have defined circulation at a distance r along a closed curve, which is basically a circle in this sense. Okay, And then what I'm trying to say is the boundary condition says that my circulation, which is defined by this, is finite. So this is finite, okay, as this is finite where? This is finite at r tending to infinity or at rs basically, okay. So this means that the boundary condition states that at, as r tends to infinity, my gamma at r tends to infinity is basically some gamma naught. The finite value means it has got some value of gamma naught. Okay. This means what I can write that my 2 pi r u theta r, okay, and when this quantity goes and when r tends to infinity, this quantity basically becomes equals to gamma naught. Okay, and then what I can now do is I can substitute the form of u theta that we basically got. Okay, so so what is that? So u theta has this particular form, if you remember. U theta has got this a1 by r plus a2 times r bar 1 minus r bar 1 minus re. Okay, and just remember this, since we are dealing with non-dimensional quantities, these radiuses that I have just shown, this would be basically r bar. Okay, so I'll just write it here. This would be r bar because of the fact that we are doing things all non-dimensionally. So this will just be r bar. That's the idea. Okay, and then we'll just substitute the form of u theta. So this is just going to be 2 pi r bar. U theta is what? I just still forgot. Sorry. It is basically a1 by r bar plus a2 times r bar into 1 minus re. That's the idea. Okay, so it is a1 by r bar plus a2 r bar times 1 minus re. I think that's it. That's u theta bar. Okay, and this is equal to some gamma naught. Okay, now what I can do is I will just multiply it by r bar, so it just becomes a1, and I'll just take this 2 pi basically here because it is just a constant, so it becomes a1 plus a2 r bar 2 minus re, and this is equal to gamma naught by 2 pi. And since gamma naught is just an arbitrary constant, gamma naught by 2 pi is still going to be is anyway going to be another arbitrary constant, and then I'll just write it as gamma naught bar, meaning that this is just an arbitrary constant. That's the thing, since gamma naught is an arbitrary constant, which means I have a new, from the definition, not definition, from the fact that I have considered that the circulation is finite, when we move a distance which is farther away, which is far away from the cylinder, the transform boundary conditions now happens to be a1 plus a2 r bar 2 minus re is basically equal to some gamma naught bar. Okay, that's it. So that's how the transform boundary condition for u theta appears to be if I use circulation, which is obvious, which is finite, at far field as a boundary condition. Okay, now so that's one boundary condition, and the second boundary condition is again like u theta at r bar equals to 1. This is equals to 1 basically. U theta bar at r bar equal to 1 is basically 1. So this is this is, let's say, so what's the equation? Let's see, what did we say? Okay, I call it as 5a and 5b. I will now name it as 5 what c and 5d. Okay, so now you can appreciate that. And of course u theta is known. U theta is just a1 by r bar plus a2 times r bar to the power 1 minus re, basically something like that. Okay, so the bottom line is that now you can appreciate that if I use this, so if I say that, okay, if I say that, and of course this remember this boundary condition is at r bar going to infinity. Okay, so this means that you can now see that for Reynolds number less than 2, if I say that this term has to go to a constant, okay, if this term has to be a constant value when r bar goes to infinity, this means that a2 has to be equals to 0. And that is obvious, right? For of course in the region where Reynolds number is less than 2. Because if my Reynolds number is less than 2, then 2 minus that quantity is obviously greater than 1, which means that if I want to have a finite quantity in the right hand side, when r bar goes to infinity, a2 has to be equals to 0. Okay? That, so that's what I was trying to say, that for Reynolds number less than 2, for circulation to be finite, circulation to be finite, okay, a2 has to be equals to 0. That's it. Okay, a2 is just 0. And then you can use the boundary condition, okay, on the surface of the cylinder to basically get the value of a1. Okay, which means that we have reached a closed form solution, okay, for a, for a greater parametric space of the Reynolds number. Now we can go up to the fact that when Reynolds number is equal to 2, that is analytical solutions are possible for Reynolds number equal to 2 if we use the fact that my circulation is basically finite at far field, and that's how we have proved. Okay, but as you can see, for Reynolds number greater than 2, okay, of course analytical solutions is still not unique analytical solution is still not possible because of the fact that I am saying that my right hand side is finite. But if I now choose Reynolds number to be greater than 2, this term become less than 1 to be precise, which means that which means that when r bar basically goes to infinity, okay, this term will anyway disappear, meaning that I cannot uniquely determine the constants a1 and a2 to be precise. Okay, which means that for Reynolds number greater than 2, it is it is still not possible to obtain closed form analytical solutions. Okay, but you can appreciate that we have moved a little bit step ahead. That earlier we said that for Reynolds number less than 1 we can only derive analytical solutions. Now we say that okay, now we can increase the parametric space from 1 to 2 by using the boundary condition on circulation to basically get the fact that okay, for Reynolds number less than 2 at least, okay, we can have closed form analytical solution using the fact that my circulation is finite when we move far away from the surface of the cylinder. Okay, that's the idea I want to convey from this stronger from this I would say it's a stronger criteria for determining unique solutions for this particular analysis. So this is something that I want to convey. Okay, I will end this discussion on these 2D flows with a particular note, and I think this would be useful for many of you who want to study more on this circulation and all these thing aspect or all these aspects. So I will basically write a note. But yeah, before that, I'll stop here for a couple of seconds. Like if you have any doubts, you can ask me, or else I'll end this discussion on 2D flows by quickly giving two notes on circulation. Okay. All right. So if no question, okay, here is one thing that I want to state on circulation. So when I define circulation, I say that circulation is nothing but it's a line integral of any, so it's a line. So in fluid mechanics, circulation is nothing but a closed, I'm integrating the velocity vector along a closed curve basically, and mathematically it is just this integral, it is the closed line integral of v dot dl bar. Okay, where as I said, this I must have a arbitrary closed curve, and then I am just integrating I am just integrating my velocity vector along this along this dl bar basically. Okay, to I'm integrating this along this curve to get my circulation. Okay, now what I can do is there is something which is known as the Stokes theorem. Okay, so if I if I apply Stokes theorem. So a Stokes theorem basically transforms the closed line integral into a surface integral. And if I do that, what I will get is I can then write it as a surface integral, okay, of curl of V, okay, dot dA, where dA is nothing but, so it's the elemental area. So remember, this dA is the elemental area, okay. So this dA is the elemental area enclosed by this closed curve as a perimeter to the area that is basically being enclosed. Okay, so I hope you understand what I'm trying to say. So what I'm now doing is, instead of writing this as dl, I'm saying it is nothing but the curl of my velocity dot the elemental area dA, okay, which is basically being enclosed by this, by this by this closed curve, to be precise. Okay, now here is the advantage of, using the Stokes theorem. Now I know that if my v is the velocity vector, so it's the velocity vector field, then I know that curl of v is nothing but my vorticity, which we call it as omega basically. So this is omega, which is vorticity, which means I can also represent circulation in terms of vorticity as the surface integral of omega dot dA. Okay, that is another definition of circulation. And this is nothing but so this means the circulation can also be defined as, I'll write it down, it can also be defined as the flux of the vorticity vector, flux of the vorticity vector through a surface S. Because remember, when we say it's flux always has to be through a surface, because otherwise there is no sense of defining a flux. Okay, so this is another definition of circulation, that yes, I know that circulation is line integral of the velocity field. It can also be defined as the surface integral of the flux of vorticity, which is basically like, omega, which is basically the surface integral of omega dot dA. Okay, that's, another way of defining circulation. The second note is that, and I'll end this discussion by just stating the second note, is that if, if I have a conservative vector field, if I have a conservative vector field, say E, okay, well, instead of defining V, let's say I have a conservative, I define another vector field, let's say E, then for a conservative vector field, circulation is always zero. That's okay, that is something that you must realize. Okay, so if my vector field is conservative, it means that my circulation is always zero. The reason behind this is because of the fact that you start from any point and you move around the closed curve and come back to the point that is always zero, and that is the definition of a conservative of a conservative field, to be precise. Okay, and since if you integrate that vector field along that closed curve and come back to the same point, and for a conservative vector field that is zero, this renders the fact that circulation has to be zero, because that's the very definition of circulation. Okay, this means that gamma is zero, which means that if I integrate this E dot dl, if I integrate this E dot dl along any closed curve, that's basically equals to zero. Okay, okay, and this is equal to zero always. All right, for example, you know electric field is one such kind of vector field which does not have any circulation. So if you integrate electric field along a closed curve, okay, that always gives you zero, meaning that the integration So integration along a closed curve equal to 0 means that if you integrate electric field along any 2 points, it is independent of the path you take basically. And that's the definition of a conservative vector field. For instance, like the electric field. Okay. So for example, this E that I wrote, this can be my electric field. Okay. This can be my electric field. And then we also get one more important, property from this. Now, since, you know, if I integrate electric, let's say electric field along a closed curve that is zero, that is something that we saw. And now if I apply the Stokes theorem, I can basically say that, okay, it is close, it is integ. So if I now apply if I now apply the Stokes theorem, I basically need to integrate along a surface, but I now need to integrate it curl of E dot dl, and this is 0. And then for any generic surface, I can simply write that curl of E is basically equals to 0. Okay, and that's one of the most important property of a conservative field, that for a conservative field, if you calculate its curl, it is always 0. And that's the reason why you can always write electric field as a gradient of a scalar potential. Okay, and that is the reason why you can always write E as minus grad of some potential phi, and this phi we call it as the electric potential. Okay, so I hope you can now draw the idea basically. So if I have a conservative field, its curl is always 0, and if its curl is 0, okay, then you can write it as a gradient of a scalar function basically. And that scalar function is sometimes called as the potential. And if in case of electric field, if you're saying that, okay, curl of electric field is 0, which is the case, then you can basically always write electric field as a gradient of a potential, and that potential is the most used potential that we use, and that's what we call as that's what in the literature is most commonly called as the electric potential. Okay, but this is where actually the math comes from, that why and how can you write a vector field as a gradient of a potential. And the reason that it has to be curl free, or it has to be a conservative vector field, or you can say that the circulation is basically equals to 0. Okay, for instance, if I have a irrotational, if I have an irrotational fluid, that means that I can say that curl of V is 0, and that's the only point where I can define a velocity potential, if you remember, which we also call it as phi basically, which was the velocity potential. But the idea is just the same, that my velocity field becomes conservative only when, only when it's irrotational, meaning that my cardinal velocity is 0, and then, I can write my velocity field as a gradient of a scalar function basically, which in fluid mechanics we call it as the velocity potential. Okay, so so that's the idea behind circulation, and this is something that I want to convey, before finishing this. And I hope you understood what I tried to say. I hope you understood the boundary condition on circulation. How do we use the boundary condition on circulation to, get a little bit stronger criteria for, getting analytical solution to the problem. And then, we ended it by taking two notes on circulation, that first, we can, relate circulation also in terms of vorticity, and then also for a generic, conservative vector field, the circulation is basically equal to 0, and then you can basically write the vector field as a gradient of a potential. Okay, that's the idea that I want to convey. All right, so we'll end the discussion on this here, and then we'll begin by discussing this week's this week's like discussions. And I think this is also a part of the week on lubrication theories and creeping flows, on the assignments of lubrication theories and creeping flows, and we will see certain aspects of that. And I hope things will I mean, things would get clarified if there are any doubts. But before starting, and before me formally laying down the agenda, if I'll stop here for a couple of minutes. If there are any questions, you can feel free to, ask. Okay. All right. If there are no questions, if uh, and yeah, like needless to say, if you have any questions during the course of the week when you are, watching these videos or when you are solving the assignments at your own time and space, and if you have any doubts, please use the discussion forum to basically, clarify those doubts. But yeah, so now what we will do is we will start off by seeing a different types of flows now, which we call it as the creeping flows, as you can see this from my screen. And we will try to understand what creeping flows are. Maybe in the week's tutorial you have solved a problem which is known as which is one of the most elementary problems on creeping flows. That is, you calculate something which is known as the Stokes drag. You basically calculate the drag force past the sphere, which is subjected to a uniform flow. And then you see that that drag is essentially a combination of two. So it basically comes out to be 6 pi eta times times its radius, and that's what you see. And then you see that uh, this the drag that you see, it it is actually a combination of the form drag and the pressure drag, and the ratio is, I think the ratio is just 2/3, and that's I think that is one of the part of the assignment questions that you are also supposed to do. But yeah, so I think that is something that you saw it in at that you saw it in the week's tutorial. But having said that, we will try to understand more on these creeping flows and why they are so popular, and and why the analysis of creeping flows are essential. These are I mean, I wish to discuss these things, which will basically give you some additional flavor of why you are basically trying to understand and trying to study these kind of flows. And we will see one of the important consequences of creeping flow problems is that the governing equations are linear, and we will basically prove that now, very shortly. And we will see certain we will see certain important consequences of linearity in creeping flows, and we will see that these we will see that the because of the fact that the governing equation is linear, some amazing conclusions can be drawn in creeping flows, which was earlier not possible if we bring inertia into the picture. Okay. And we will formally define that what exactly is a creeping flow very shortly. But I think by now you know that, and also by the week's contents you know that the flows which doesn't have basic which do, in which the Reynolds number basically goes to zero are creeping flows basically. Okay. And you will basically see that because of the fact that we don't have inertia, the governing equations are linear, and the fact that the governing equations are linear have lasting impressions on certain conclusions. And we will see that how I mean when and how these kind of what you say general, I mean, observations can be made in creeping flows based on the linearity of the governing equation. Okay. And we will see that shortly. But so with that, let's try to understand. So in order to understand the creeping flow limit, that is when Reynolds number tends to zero, I will start off by writing the general momentum conservation equation in vector form. That is the Navier-Stokes equation in vector form containing the inertia terms, and from that we will try to derive the creeping flow limit basically. Okay. So so we'll begin by deriving the creeping flow equation. So what I'll do is I'll start off by writing the Navier-Stokes equations first. Okay. And I'm writing this in vector form, and I'm writing this in first of all I'm writing this in dimensional form. Okay. And when I'm writing in dimensional form, note that any quantity where I give a dash, that's dimensional. Now that's the other way around. Okay. So if I have a quantity, let's say u bar, which is let's say my velocity field. Okay. And I give a dash, that means it is a dimensional, you know it's a dimensional quantity. Please note that. Okay. So then my Navier-Stokes equation becomes basically what? So it is rho times, that's simple, right? We have been doing it many a time. So it is just del u dash by del t, where dash is nothing but my dimensional quantity. That's it. The idea of writing dash is that since we'll be mostly dealing with non-dimensional quantity, I want my non-dimensional quantity to be, little bit simplified, and that's why we have written the dimensional as dash, and we'll write the non-dimensional as just anything without a dash. Okay. So it is rho times del u dash by del t dash plus, and remember this is a vector, okay, because I'm writing the Navier-Stokes equation in vector form. So this becomes u dash dot grad of u dash, okay, all right. And then I have what? I have the pressure gradient, which is minus gradient of P dash plus mu del square u dash, okay. That's it. I'm just not considering any body force, okay? And also I have my continuity equation, which is divergence of u dash is equals to 0. Okay? Alright. So let's now, before deriving the tripping flow limit, let's just, non-dimensionalize this equation, okay? So I will non-dimensionalize my u dash as a non-dimensional u by uc, okay? Where uc is basically my, characteristic velocity. Okay? I hope this is fine. Then I'll non-dimensionalize my time t dash as just t by tc, where tc, let's say, is any characteristic time. It can be the advection time scale, it can be the diffusion time scale, or it can be, the prescribed time scale of the problem that we already have. Okay, it can be anything. And then I also need to, define my del. And remember, these gradients are also dimensional. That's why I'll just represent it as dash. This will be dash, and this will be dash. So the non-dimensional gradient is just going to be, oops, I think I wrote it the other way around. This is non-dimensional, so this will be dimensional by UC, and this would be dimensional time by TC. Sorry for the mistake. And then my non-dimensional gradient would be the dimensional gradient by LC, which is where LC is nothing but my length scale. Okay, so needless to say, but I'm just writing it. So this is my characteristic velocity scale. Okay, this is my characteristic, characteristic time scale, and this is my characteristic length scale. Okay, all right. So let's use this characteristic scale basically to non-dimensionalize this equation, and let's see what do we get. Okay, so I'll get what? I'll get rho times, from here I'll get UC by TC, okay, times del U bar by del T plus, what shall I get from here? Okay, I'll get UC square by, I think I'll get UC square by LC, okay, UC square by LC, U dot grad U, okay, and then I'll get minus of PC by LC, okay, gradient of P plus mu UC by LC square del square U, okay, I think that's it. And now what I do is I choose my characteristic scale for pressure as the viscous scale, which is, so I'll choose PC as mu UC by LC, which is nothing but the viscous scale for pressure. Okay. If I do this, then this term becomes what? This term becomes mu UC by LC square. Okay. All right. Which means that my pressure gradient basically scales as del square U, basically. That's what I'm trying to say. Alright, so now what I will do is I'll multiply the entire equation, hoping to get a non-dimensional number out of it. I'll multiply the entire equation by LC square by mu UC. That's what I will do, okay? So multiply by LC square by mu UC. Okay. So if I do that, what shall I get? So these terms would just go out to be equal to 1 because they are just the same term in the, they are just 1 by of the same term. So they'll just give us 1, which is fine. And then I have these terms, okay? So I have rho UC by TC into LC square by mu UC, okay? That's the inertia term, and then I have del U bar by del T, plus I have this term, UC squared by LC, okay, into LC squared by mu UC, okay? And then I have the advective term, which is U dot grad U. And the others, they are just minus gradient of P plus del square U. Okay, I hope you are with me so far. It's just the non-dimensional that we have done again and again so far in this course. Okay. All right. So if I simplify, then let's see what do we get. So I think this UC and this UC cancels here, and then I have this LC and this LC. And okay, I should also have a rho here because the rho should be multiplied on both these terms. That's because the rho is multiplied outside the bracket. That's the reason I have a rho here also. And then if I rearrange this term, let's say what do I get? So if I rearrange, I get rho LC square by TC, and this is mu, okay, times del U bar by del T plus then this UC, I think this UC and one UC will get cancelled, which means it is rho UC LC by mu, okay, U dot grad U, okay? And then this is minus gradient of P plus del square of U. Okay, now what I will do is I will choose TC, which is my time scale, as my advection time scale, which is LC, which is just LC by, you know, UC, meaning that I'll just choose my time scale as my as my advection time scale. Okay, this is my advection time scale. Okay, and if I do this, basically I'll just substitute this TC here. Okay, so this just becomes rho LC squared by LC by UC. Okay, and then I have this mu that is still there, and then I have del U bar by del T plus rho UC LC by mu. Okay, U dot grad U. Okay, and then I have minus gradient of P plus del square of U. All right, so if I just simplify this becomes, so this goes and then UC goes above. So basically I have what? I have rho UC LC by mu, okay, and this is del U bar by del T plus rho UC LC by mu U dot grad U, and then the same terms on the right hand side. All right. So after this match, so what do we get? So now here it gets interesting. So now what is this basically? Rho UC LC by mu. So this is nothing but the Reynolds number corresponding to the length scale LC. Okay, and this is also nothing but, you know, the Reynolds number, which means, okay, which means I can now write this as, which means I can now write this as Reynolds number times del U bar by del T, okay, plus U dot grad U, okay, and this is equal to minus gradient of P plus del square U. Okay, so that's the non-dimensional equation that we basically get. That's the non-dimensional momentum equation. In fact, this is what the momentum equation turns out to be if you non-dimensionalize them using the appropriate scales that we have just that we just saw. Now the important thing is, if I now choose that, so there is this limit. So in the creeping flow limit, okay, in the creeping flow limit, I can say that my Reynolds number basically goes to 0. Okay, and that means that my inertia is very much less dominant with respect to the viscous forces, which means I can straight away say that this term basically goes to 0. Okay, which means that the equation reduces to, the momentum equation now reduces to, in the limit when Reynolds number goes to 0, which we also call it as the creeping flow limit, as just minus gradient of P plus del square U, that is equal to 0, and of course I also have the continuity equation, which is divergence of U to be equal to 0. So that's it. That's the creeping flow equations, okay, that you guys saw it in the theory classes, and this is how it comes from, the non, then that's the, once again you can appreciate the power of non-dimensionalization. Okay, from the dimensional equation you just can't say anything directly. Okay, you can, of course, you can say that density is this and that and viscosity is this, but that doesn't give you a clear idea. But now you can pinpointedly say in terms of the Reynolds number that, okay, if my Reynolds number basically goes to 0, then these terms, since this is an order 1 term, basically if I say that my RE basically goes to 0, which means that this term is now very much less dominant over these two terms, meaning that I can just drop this term off in the limit when RE tends to 0, and this is known as the creeping flow limit, as you guys know. Okay, and in the creeping flow limit I just don't have this term, and then my equation of motion are just minus gradient of P plus del square equal to 0, and divergence of U is basically equal to 0. Okay, so this, so the equation that you saw here, these are known as the creeping flow equations, and so these are known as the creeping flow equations, and sometimes they are also known as the Stokes equation basically, and sometimes they are also called as the Stokes equation. Okay, all right, I'll stop here for a couple of minutes. I hope you understood how we basically took the power of non-dimensionalization to, derive the limiting case of creeping flows by equating, by, it's not equating by, but by saying that the Reynolds number basically goes to 0, and then we neglect the inertia terms to, establish a balance. So you can appreciate that now in the creeping flow limit there is always a balance between the pressure gradient and the viscous term basically, and both of these balance each other, and that's why we say that their sum is basically equals to 0. Okay, and of course we always have the continuity at our disposal basically. But these are this is how we derive the creeping flow equations in fluid mechanics basically. I'll stop here for a couple of minutes. Please let me know if you have any questions on this. All right. If no questions, see, knowingly or unknowingly, we got an amazing, simplified equation from, a very complicated equation like of this from. That is simply because when I say that my Reynolds number basically goes to 0, we basically discarded the inertia term, which stems from this non-linear term, which is U dot grad U. Okay. Uh, for the time being, the temporal term is still linear, but this is the main source of non-linearity, which comes from inertia basically. But once we say that Reynolds number basically goes to 0, meaning that this term identically now is not, I mean, it's not identically, that's not correct to say, but it's like in the limit when Reynolds number goes to 0, this term is no longer dominant, which means we can discard the term in the momentum equation, which is the main source of nonlinearity. Meaning that in the creeping flow equations, since I don't have the nonlinear term, the creeping flow equations are essentially linear. Okay, this is one of the most important, conclusions, or it's not conclusion. This is one of the most important characteristics of the creeping flow equations. Okay, the equations are linear, and the consequence of this linearity is amazing, and we will just see very shortly. Okay, which can't be predicted, and these consequences can't be predicted if we have inertia into the picture. Okay, so the equations are linear basically. That's what that's the first and foremost thing that we can observe in creeping flow in the limit when in the limit of creeping flows. Okay, all right. So that's linear because the only source of linearity in the Navier-Stokes equation is the fact that this u dot grad u terms, and in the limit when Reynolds number basically goes to 0, then we can simply discard this term, which is the main source of nonlinear. So I don't have the nonlinear term now in my equation, and thus the creeping flow equations, which establishes just the balance between the pressure gradient and the viscous forces, they are indeed they're indeed linear. That's the idea. Okay. All right. Now, what we will see that because these equations are linear, they have they have some very important consequences, and we will see that, and we will now see that. Okay. So the first consequences, the first consequence of these, the first consequence of this, what to say, of this linearity is as follows. Okay. So I have taken this example from the book by L. Gary Lynn. So I'll write it down here. So this is from, so so it's important to duly cite it. So this is from the book of, so this is this so there is this book called Advanced Transport Phenomena, and this is from that book. So I'll write it down. So I don't have the exact, okay. So this is from the book of L. Gary Lynn. The name of the book is Advanced Transport Phenomena. That's the name of the book. Uh, I forgot the edition, but the publisher is Cambridge University Press. Okay, you can have a look on this. But yeah, so this example I have taken it directly from this book, uh, and that is something that we will see now. Okay. Anyways, so So the idea is that we will see the consequences of the creeping flow equations, that uh, because of the fact that they are linear. Okay, and the first consequences is that we will estimate the drag in the limit when we have a creeping flow. We'll estimate the drag on bodies that are mirror image in the direction of motion, meaning that if I have a body, let's say of this shape, and I have another body which is just the mirror image of this body. Let that if I just put a mirror here, this object is just the mirror image of the object, of the object to the left hand side. Okay, the idea is that in the creeping flow limit, okay, we will estimate the drag on these two objects, and let's say you know so the idea is that will the drag, let's say that if the drag on A is dA and the drag on B is dB, then qualitatively at least can I comment on the magnitude of these drag forces. Okay, that is dA greater than dB, or is dA less than dB, or is dA equal to dB. Okay, in the limit when my Reynolds number basically goes to 0, that is in the creeping flow limit. Now, if inertia were into the picture, you could have easily said that this object will experience a greater drag, okay, because it seems like a bluff object in the direction of flow rather than this object, because this happens to be a streamline object with respect to the flow direction, okay. But if I consider this object, this happens to be a bluff object, so naturally, our intuition says that dB has to be much larger than dA because of the fact that we encounter a bluff object in the direction of flow. But we will see that in the limit of creeping flows, that their drags are exactly going to be the same. Okay, and this is the reason, and I'll say you that, and I'll prove you, and I'll try to convince you why this is the reason. Okay. Okay. So before understanding, of course, it is will not be able to prove this mathematically, at least at this point of time. You can do that, but we'll not do this now. But qualitatively, at least, I'll try to argue that their directs are going to be exactly the same in the limit of creeping flow analysis. That is when my inertia doesn't come into the picture. Okay. Okay. For that, let's consider the case A. Okay, that's the first case. That is for for this object. So for this object, let's say for object A, if I write down the equations for I mean the equations which governs the motion, they are nothing but the creeping flow equations, right? Which is nothing but minus gradient of P plus del square U is equals to 0. Okay, and divergence of U, that is equals to 0. And so these are the equations, and they are subject to what? They are subject to the fact that u is basically some far stream velocity, let's say capital U, which is basically this. So a velocity is some far stream velocity at r tending to infinity. Okay, and u is 0 on sp means on the part on the surface of the object. That's that's the idea. Okay, so all I am doing is I am just writing the governing equations which governs how the flow field would would look like when there is a uniform flow moving past the object A. Okay, which is basically this object that is the object that I'm encircling right now. Okay, now let's say for the time being that I know the solution. So what are the unknowns here? So the unknowns here are the velocity field u bar and pressure. Okay, and let's say by some means using these two boundary conditions, I solve these two equations. Okay, that is the momentum, that is the creeping flow equations and the continuity equation. And I say that I obtain the set of unknowns u bar and p bar. Okay, so meaning that by some means, don't ask, like, let's not consider how did I do it, but I just say that by some means, okay, I solve these two equations by using the appropriate boundary condition as we saw, and the solution is just u bar and p bar. Okay, so let's say these are solutions of A. Okay, now if I look at this flow, the flow in B, the flow in B can exactly be recreated if in A I say that the uniform flow, instead of coming from left to right on the screen, it is now coming from right to left. That is in this direction. I repeat, I'm saying that the flow field in B, which is this, can be exactly recreated if I say that in A, instead of the uniform flow coming from left to right, it is coming from right to left. Okay, that is fine. That can be physically done, right? Instead of instead of putting the cone like this, instead of putting the cone, instead of putting the back of the cone at front and the front at back, I can say that the flow is coming from the other end. That is exactly fine, right? Then I can argue that if that is the case, the fact is that if the flow is coming in the other way direction, then I can say that minus u bar and let's say minus p are the solutions of B, right? Now this I can say only because my governing equations are linear. I repeat that if I reverse the flow field, if my governing equations are linear, I can straight away say that if the earlier flow field was u, if the earlier solution to the flow field was u and p, then the solution to the reverse flow field is simply going to be minus u and minus p, which is nothing but the solution if I have an object which is just the mirror image of the first case. And this is possible because of the fact that my governing equation, which are the creeping flow equations, they are linear. Okay, so you can write this: since my governing equations are linear. Okay, Now, since minus u and minus p are the solutions of this field, okay, that means the drag force, the magnitude of the drag force will be the same, right? Because the solution has only differed by a sign, not its magnitude essentially, which means that the magnitude of the drag force in solution A will exactly be equal to the magnitude of the drag force, okay, in, or how do I write? So the drag force is written as dA, so I'll write it as dA only. So the magnitude of the drag force in solution A is exactly going to be the magnitude of the drag force in solution A, because their solutions only differed by their solution just differed by a sign only, right? Because I already stated that since the governing equations are linear, the problem B can be uniquely recreated if I just change the, change the direction of flow of problem A basically. Okay, so this means that my drag forces in the two cases, although they seemingly appear that the drag in B will be greater, in the limit of creeping flows the drag forces will essentially be the same. Okay, this means that the drag forces are equal. Okay, the drag forces in the two cases are equal, are equal. And this is only because of the fact that my governing equations are linear. Okay, if the governing equations are non-linear, for instance, if I have inertia, then my governing equation will no longer be linear, because I will have that u dot grad u term, and then you cannot say, and you cannot basically do this analysis. Okay, uh, uh, because of the fact that my governing equations are now non-linear if I have inertia into the picture, and it is essentially inertia that is responsible for having a greater drag in case of case B. Okay, it is essentially inertia that essentially leads to a greater drag in case B, but since now we don't have inertia into the picture, the drag forces will just be the same in the limit of creeping flow analysis. Okay, so the drag forces into are equal, uh, owing to, I'll just write it down, owing to the linearity of the creeping flow equations. Okay, all right. I hope you can appreciate like how, like, I mean, because of the fact that the creeping flow equations are linear, you know some important, qualitative assessments can be done which were otherwise impossible, or which are otherwise next to impossible if I have inertia into the picture. Okay, and this again, all of these again boils down to the fact that my governing equations are linear. The governing equations which govern which govern the flow of the fluid in the creeping flow limits, they are linear basically. Okay, and one such example is the drag on objects that are mirror image in the direction of motion basically. Okay, and sometimes this is also known as 4f symmetric. Basically the problem is 4f symmetric. Okay, and see, if the problem is 4f symmetric, all these forces like the drag forces, like the different drag forces, or in this case there is no lift, but yeah, we'll have a drag force here, but you can say that these forces are exactly the same if I have a 4f symmetric problem. Okay, all right. The second consequence is, so we will see the second consequence, but before that, if you have any questions, I'll stop here for a couple of minutes. If you have any questions, you can ask me on the first example that we just saw. I hope these are interesting things, because these are the things that we didn't expect in regimes where we have inertia into the picture. Okay. Okay, all right. So the second consequence is that we will now try to estimate the lift on a sphere that is rotating in a background shear flow basically. Okay, for instance, what I have in my problem is that I have a sphere which is rotating, about some axis with some angular velocity omega, subjected to a linear shear flow of this form. And in this case, in the limit of creeping flows, they are asking is that will the sphere have any lift forces or not? Okay, is something that we will you know try to answer at least qualitatively by understanding the linearity of the creeping flow equations. Okay, all right. So again, this is simple, and the argument is the same. That is the linearity of the equations. But like here is how we will put forward, the argument. Because of the fact that of the fact that my creeping flow equations are linear, I can, and we saw it multiple times, that if I have equations that are linear, I can decompose the problem into two simpler problems or many simpler problems. Like that is only possible if my equations which govern the dynamics, they are linear in nature. Okay, and since the creeping flow equations are linear, what I can now do is I can decompose this entire problem into three problems. Okay, I'll call these individual problems as A, B, and C, as you can see from the screen. Okay, the first problem is that there is just a sphere which is just rotating in a stationary fluid. That is first problem. Okay, the second problem comes from the decomposition of the shear flow, is that the shear flow is decomposed into a uniform flow. Okay, plus a pure shear flow which basically doesn't impart any kind of lateral motion to the sphere. Basically, that the sphere center and the center of the flow coincides each other. That's the two that's the other two decompositions that we'll do. I hope you understand. So what I'm doing is I'm just decomposing this into a uniform flow, which is this, plus a flow which doesn't impart any net motion, any net push to the sphere, because of the fact that this flow will just give the sphere a constant vorticity only, without moving the sphere forward. And the other two individual problems, I'll call it as problem B and problem C. Okay, I hope you understood how the decomposition is done. So there was a sphere which was rotating with some omega in a shear flow, in an off-centered shear flow, I would say. What I will do is I will try to, and of course the objective was to find that the lift on the sphere, is there any lift that this sphere experiences, okay, in the limit of creeping flows. Now, in order to understand that, okay, what I will do is, since I know that the creeping flow equations are since the creeping flow equations are linear in nature, uh, since the uh, since the equations which govern the dynamics are linear, we saw this multiple times, that I can decompose any problem into simpler problems, to be precise. Okay, and the simpler problem that I have decomposed is that there's a sphere which is rotating in a stationary fluid, plus a stationary sphere in a uniform flow, plus a shear flow which shares the same center with that with that two of a stationary sphere. Okay, these are the three simpler problems into which I will decompose the actual problem into. And you can see that if you just club these three problems together, together, you end up getting the same original problem that we are essentially trying to solve for. Now, what you can appreciate, that since the governing equations, which are nothing but minus gradient of p plus del squared u, this is 0, and divergence of u, this is 0. Since these governing equations are linear, what I can say is the fact that the lift, if calculated in the three individual cases, LA, for instance, a sphere, you can appreciate that a sphere which is just rotating in a stationary fluid, okay, this that sphere will not generate any lift. That sphere cannot generate any lift all by itself, basically. So La, that is the lift force, in case of case A, this is 0. The second case, there is just a stationary sphere in a fluid which is having a uniform far field velocity. Okay, now in this scenario, that is the case B, a stationary sphere subjected to a uniform flow, the lift is just 0, and this is just the and I believe this is just the Stokes problem that you solve. There will just be a drag force. The drag force is just going to be 6 pi mu times u times the the radius of the sphere, which is a, basically. So there won't be any lift force in case B as well. Only the force that will so it will just so in case B, the sphere is just going to have a drag force. That's the idea, and that's the Stokes drag that you just calculated. Okay, but no lift force, because you can understand that there is no mechanism which can generate lift in this manner. And also in case B, there won't be any lift force, because you can understand that this shear flow, which has the same center with depth of a stationary sphere, what this shear flow will do is, you can prove that it will not exert any net force on this sphere. Uh, it will exert a net torque. So basically, what you will see that in the limit of creeping flows, this far field shear flow will basically impart a rotational velocity of omega equal to half. If not half, basically it should be equal to the shear rate times 2. This much will be the rotational velocity of the sphere, okay, in the limit of creeping flows. Okay, meaning that this shear flow will just impart a constant vorticity to the sphere. I mean the vorticity, and that's not correct. What I mean to say is that the vorticity of the far field flow will just impart a constant angular velocity to the sphere using something which is known as the hydrodynamic torque free condition. Okay, but in any of these cases, the lift also in case C is 0. Basically, it will not impart any lift. It will just, at max, what this flow can do is it can just rotate the sphere with some constant angular velocity. Okay, all right. This means that if individually, since the net lift forces of the individual problems are 0, that means the total lift, which is L, which is just the summation of LA plus LB plus LC, okay, this has to be equals to 0. And this is once again because of the fact that my governing equations are linear. Okay, this is once again because of the fact that my what do I say, governing equations are linear. Okay, so since my governing equations are linear, I decompose this problem into simpler problem, and I argue that the lift forces of all the simpler problems, of which I have decomposed the original problem into, the lift forces of all the smaller or the decomposed problem, they are 0. And since the individual problems doesn't have any lift forces, I can add the lift forces together because the governing equations are linear, and then the total lift force is just 0, which means that the lift force of a rotating sphere in a off-centered shear flow is 0 in creeping flows, in the limit of creeping flows. But again, this is not possible if I have inertia into the picture, and there are papers which shows that indeed the sphere experiences a lift if there is a inertia, and even if there is weakly inertial forces, the sphere will experience a lift. And there are papers which basically shows this physics into the picture. If there is even if there is a weak inertia that comes in the picture, but if there is no inertia that is in the limit of creeping flows, the sphere won't experience any lift. Okay, that's the idea of the linearity, and that's another beautiful consequence of the linearity of the creeping flow equations. Okay, all right. And similarly, I'll end these consequences by just stating one more example, that if I now have a sphere, okay, that is basically placed in an off-centered position with respect to a possible flow, the lift of this sphere will anyway, and of course this sphere is basically bounded by channels because of the fact that I have a possible flow. The sphere won't basically suffer any lateral migration in the direction, normal to the direction of the flow in the limit of creeping flows. Okay, so that's another consequence, that there won't be any lateral migration of this sphere, okay, when subjected to a possible flow in the limit of creeping flow. And the idea is very simple, that if I reverse the direction of the flow, the sphere, the problem just becomes 4f symmetric, just like the problem that we saw it in the first case. Okay, that is the mirror image, that the objects, that if I say that, okay, my flow field is coming out from the other direction, then the solution is just the negative of the solution to the of the solution to the other problem, meaning that the problem is just 4f symmetric basically. And since the governing equations are linear, this can be done, and that's why if in the first case there is no lift, then it cannot happen that if I reverse the direction of the flow, if it will generate any lift forces. Okay. uh, Again, because of the fact that my governing equations are linear in nature, which means that the sphere won't suffer any lateral migration when subjected to a possible flow if I don't have inertia into the picture, or we are in the limit of creeping flows. Okay. That's that's another idea of looking into the consequences of linearity of this picture. Okay. So So what I'll do is, I'll before ending this, in the next class, we will solve a problem similar to the Stokes drag problem. That is the drag on a sphere that is subjected to a uniform flow. Now what we'll do is we'll try to see that if I will first try to see what is the drag that a sphere will experience. Instead, if the flow is, of course, in the limit of creeping flows, we'll try to estimate the drag that the sphere would experience if now I have a parabolic flow in case of a uniform flow. Okay, that is dynamics of a sphere in presence of a parabolic flow is something that we will try to we will basically try to uh, study it in the next class. And for studying that, okay, we will use the same creeping flow equations, and we will solve basically the biharmonic equation that the stream function satisfies. Then this is something that we have already done for the Stokes problem. We will extend this to the parabolic flow problem. The procedure will more or less be same, but the parabolic flow will generate certain complexity, and we will see that we indeed have the right tools basically to tackle those complexity. Okay. But before that, in order to make you feel more comfortable with the solution, we'll need to understand something which is known as the spherical coordinate system. So in today's class, before ending this, I will quickly give you a heads up of the spherical code of how the spherical coordinate system essentially operates. Okay. And then we will call it a day for this session, and we will solve the sphere subjected to a parabolic flow problem in the next discussion, that is in the next class basically. Okay. All right. So but before that, let's quickly give you a heads up of the spherical coordinate system, and this is where we will end the discussion of this is where we'll end today's discussion basically. Okay. So the spherical coordinate system basically looks, so what we'll do is we'll try to understand the spherical coordinate system and try to draw its conversions also from the basic Cartesian system. Okay, that is how is the Cartesian and the spherical coordinate system linked. Okay, so if I, let's say, have a Cartesian system, let's say I call this as Z. Okay, let's say I call it as X, and this is Y. Then in this XYZ space, I can define my something which is called as the spherical radius as some R. Okay, we'll call this R as my spherical radius. Okay. All right. We will denote, you know, we'll denote this. So we'll denote the spherical radius as R, and if I now have a cylindrical radius, we'll denote it as rho basically, and we will see how this cylindrical radius also come in the picture. But if I say R, it means it's a spherical radius. Okay. Then the angle that this R vector makes with the Z vector, this angle is known as theta, and this is nothing but the polar angle that we use in spherical coordinate system. Okay. And then if I project this R vector into the on the xy plane, I basically end up getting this vector is known as rho, and this rho is nothing but the cylindrical radius. Okay. And the angle that the cylindrical radius makes with the x-axis, this is given as phi in spherical coordinate, and this phi is known as your azimuthal angle basically. So this R theta phi, they form an orthogonal basis, and you can denote this coordinate system, and in fact this coordinate system of R theta phi is known as the spherical coordinate system. Okay. So this is my spherical coordinate system. Similarly, the coordinate system of rho, okay, phi, and z, this is my cylindrical coordinate system, as we are more familiar with rather than the spherical one. Okay, till now at least. So this is my cylindrical system. Okay, and x, y, z, as you know, they are our much familiar Cartesian sets of axes. Okay, they are my Cartesian system. Okay, now we can straight away derive certain relationship between the spherical and the Cartesian coordinate system. For instance, I can say that from this figure itself, I can just say that my z is just r cos theta, because of the fact that this is theta and this is r, so my z is just r cos theta. Then x, and then this x can be written as, so if this is r, this becomes r sine theta, and then this x becomes r sine theta cos phi. Okay, so my x becomes r sine theta cos phi, uh, is the conversion link between my spherical to Cartesian system. Okay, and similarly I can show that my y is nothing but r sine theta sine phi. Okay, that can be easily interpreted because this is r sine theta and this will now become r sine theta sine phi. Okay, so these are the convergence. So these are the convergence from Cartesian to spherical system. And also in the cylindrical sense, you can see that rho is nothing but r sine theta, where this rho, as I said, this is my cylindrical radius. This is my cylindrical radius. And r, as we all know, as I have been telling repeatedly, this is my spherical radius. Okay. All right. Okay, so that's the heads up. We will not, so I think this much information is sufficient for you to start dealing with, start dealing with spherical coordinate systems. And in creeping flow, in the analysis of creeping flow, we will be sticking around mostly with spherical coordinate system, and in fact we will be using just spherical coordinate systems only. And that's the reason why I have just given you a heads up of this coordinate system. Okay, and in the next class, we will basically be solving a numerical based on creeping flows, as I just said. So the numerical involves just calculating the drag, okay, on a sphere that is subjected to a far field parabolic flow. Okay, in the limit of creeping flows. Okay, this is something that we'll solve. That's an extended problem. I mean, that's a little bit of a bigger problem, and we will try to solve this problem very systematically it in the next class. And of course, we'll be using spherical coordinate system, but that problem is axisymmetric, so we will not have this dependence on phi. Rather, we'll just have this r and theta that will just come into the picture, because of the fact that my problem is axisymmetry with respect to the axis of symmetry, which happens to be the z axis in the problem. Okay, all right, so we'll stop here today. If you have any questions, you can ask. If not, please post your queries in the discussion forum, as you guys have been doing, and we'll meet in the next week at the same time using the same link.